Welcome to video lecture F8. This one is on diagonalization of real symmetric matrices. I'll be your leader, Tom Roby, and here are the outline and objectives. We're going to combine the geometric work we've done recently on orthogonality and projections with the algebraic work that we did earlier on eigenvalues, eigenvectors, and the change of basis to analyze the following fundamental result, which is that every symmetric matrix, every matrix which is equal to its own transpose, is orthogonally diagonalizable. So you can write it as PDP inverse, where in fact P is an orthogonal matrix. Now this is pretty exciting because we know that if generically, if you just take any matrix in R n by n matrix, it may not even be diagonalizable, much less orthogonally diagonalizable. So to have a case situation where we know that we always get diagonalizability is really quite nice. And finally, I'll give an example of how to compute this in practice. So first, let's recall a few definitions and make sure we're straight on all the terminology. So what's a symmetric matrix? Well, that means that A equals A transpose. So which of these matrices are symmetric? This one, let's see. In order to be symmetric, if I took the transpose of 1, 2, 3, 1, I would get 1, 3, 2, 1. And those aren't the same, right? So these off-diagonal entries, 2 and 3, that are symmetrically placed have to be equal to each other. So I can make it symmetric by making this a 2 or this entry a 3. How about B? Well, B, you see, the diagonal doesn't matter, right? These don't have to be the same, but the off-diagonal entries do. So this matrix is its own transpose, so that one is symmetric. And finally, if you look at this one, you can see, well, it's almost symmetric, except that, again, the 0 and the 3 need to be the same. So I either need to make this one a 3 or this one a 0. OK. So that's what symmetric means. And remember that a matrix is orthogonal if its transpose is the same as its inverse. In other words, if you multiply it by the matrix by its transpose, you get the identity matrix. And that should make some sense, right? Because a matrix that's orthogonal is one whose columns are orthonormal, meaning that the inner product of any two of them is usually 0 if they're different and 1 if they're the same. But that just corresponds, if you take U transpose times U, you're just multiplying the ith row of U. You're just taking two columns, and one of them's become the row when you take the transpose, and you're just saying that the inner product of those column vectors is equal to 0 if they're different and 1 if they're the same, and that's why you get the identity matrix that looks like this. Okay. So is this matrix orthogonal? Sure. Every column has unit length, and if you look at the inner products pairwise, you get 0 all the time. This is the nicest possible basis, the standard one. How about this one? Well, if you look for orthogonality, you find that if you take the inner product of the first and second column, that's orthogonal. First and third, you get 0. Second and third, you get 0. So the columns are orthogonal. But that's not enough, remember, for it to be an orthogonal matrix because we don't have orthonormality. So in order to make this an orthonormal matrix, we would have to replace it with by normalizing all the entries. So what I would do is say m prime is equal to 1 over the square root of 2, 0, 1 over the square root of 2, 0, 1, 0, and then 1 over the square root of 2, 0, negative 1 over the square root of 2. And that would be a matrix that when I multiply by its transpose, I get the identity. OK, now if you look at P, this isn't a good example of a matrix where all the columns are normalized already, right? Because this 1/5 means I'm dividing. This is 3/5, negative 4/5. OK, so I've basically just pulled the factor of 5 out in front because the norm of each of the vectors inside this matrix is 5. And so if I divide by 5, they all have norm 1. So the only question is, are they orthogonal? And you check, OK, well, the first and second are orthogonal. First and third, oh, whoops, they're not, right? Because 3 times 3 is 9. And so you end up with the inner product of the first two is going to be, well, 9 divided by 5 squared. So in any case, it's not, this matrix is not orthogonal. And to make it so, you'd have to fool around with it a little bit. So now remember what we did about diagonalizability. It's only something that applies to square matrix. And a square matrix is diagonal. The definition is if it's similar to a diagonal matrix, which means that it can be written as P, D, P inverse, where D is diagonal and P is invertible. But we showed that that was equivalent to A having n linearly independent eigenvectors. And in fact, the eigenvectors are just the columns of this matrix. Since they're linearly independent and there are n of them, that means that these form a basis. And so the columns form a basis for r to the n, which means that this is an invertible matrix. And then the diagonal entries are the corresponding eigenvalues. And they have to correspond. And so lambda 1 corresponds to v1, lambda 2 corresponds to lambda 1 corresponds to v1, lambda 2 corresponds to v2, and so on. Lambda n corresponds to vn. You can have repeats here in the eigenvalues. And so now the precise definition of something being orthogonally diagonalizable is that I can write it as PDP inverse for some orthogonal matrix P. But if it's true, remember that P inverse is just another name for P transpose, so I can also write it as PDP transpose. Okay, and so that, for one thing, it makes it easier. You don't have to compute an inverse. It's easy to write down the transpose, not so easy to write down the inverse of a large matrix. Okay, so here's something that shows you that orthogonal diagonalizability is not something that you would expect every matrix to have, right? I mean, ordinary matrix, we don't even expect it to be diagonalizable at all. But if it's symmetric, it will be diagonalizable. And if it's orthogonally diagonalizable, it actually has to be symmetric. Okay? And the proof of this is one line, right? Because if A is equal to PD P transpose now, right? Because P transpose equals P inverse, since P is an orthogonal matrix, then what happens when I take the transpose of that? Well, to take the transpose of a product of things, I just reverse the order and take the transpose of each piece. Okay, so the transpose of this thing becomes PD P transpose transpose, so I get P transpose transpose, D transpose P transpose. Now, if you transpose something twice, you get back where you started. If you transpose a diagonal matrix, it doesn't change it, because there's no off-diagonal entries to worry about. And P transpose is just what it is, and that's just the same thing as PD P transpose, which is, of course, A. Okay? So you can only orthogonally diagonalize a symmetric matrix. That's the easy direction. The harder direction is that, in fact, the converse is also true. So if it's a symmetric matrix with real entries, then it can always be orthogonally diagonalized. Now here's one more lemma to discuss in this context. If A is a real symmetric matrix, then any two eigenvectors from different eigenspaces will be orthogonal. Okay? So you give me one eigenvector that corresponds to 3, another eigenvector that corresponds to 2. If I take the dot product of those two vectors, I have to get 0. Right, so why is something like this true? Well, here's the start of the proof, and I'll finish it off by hand. Suppose that I've got one vector that's an eigenvector corresponding to lambda, and w corresponds to mu, and lambda and mu are different. So they correspond to different eigenvalues. Then what I want to claim is that if I look at lambda of v dot times v dot w, that'll be the same as mu times v dot w.